So last time we were talking about the derivative rules, and we had touched on most of them. Well, most of the ones you have learned in 16A so far. Just as a reminder, let's do a couple more. So for example, if we want to find the derivative of, say, x to the 7th times cotangent of x, but the cotangent of x. Sure, you can start. Okay. So the way we're going to do that is we're going to use the product rule. It's going to be, well, you can write this kind of as much or as little as you want. It's kind of nice to see your own thought process. So I'm going to kind of do it the long way first and say, well, it's the derivative of x to the 7th times cotangent plus x to the 7th times the derivative of cotangent of x. We can't stop there though, right? We actually then have to find the derivatives that we have written down. So the derivative of x to the 7th is going to be 7x to the 6th. And the derivative of cotangent of x is going to be, it sounds like noises started, negative cosecant squared of x. And if I was writing this as simply as possible, I would write it as 7x to the 6th cotangent x minus x to the 7th times cosecant squared of x. That's probably how I would prefer to write it. Why don't you all try using the quotient rule to find the derivative of x squared plus x over x minus sine of x. Seems like a good, and you don't need to simplify your answer. Just use the quotient rule to find the derivative of that. And those of you on Zoom should do it as well. Oops, I just did something weird. That's not what I wanted to do. It looks gross, but it's only fine. What's that? Yeah, it's not my favorite. So I will, well, actually, I'll say it in a minute. Yeah, we should do that. So you can actually wait. Let me do that minutes for it this way. The bottom thing times the derivative of the top. That's the top thing times the derivative of the bottom. All the bottom square. So let's remind ourselves of the quotient rule. I should have maybe used a different letter than F, but if I think of this as just the top over the bottom, then the derivative is going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. It's always the quotient rule. It's kind of a pain, but that is what it is. So here, we're going to get the bottom, x minus sine of x, times the derivative of the top, which is 2x plus 1. And then we're going to subtract, and we're going to get the top, x squared plus x, times the derivative of the bottom, which is 1, and the derivative of sine x is cosine x. And then all divided by that denominator quantity squared. And it's just kind of a thing. You probably do need to memorize it if you haven't already. It's going to come up. Yeah, it's going to come up. It's not going away. Yeah. Let's talk about a couple other things from 16A that will come up in this class. Let's see here. Where am I going to put things so I don't lose them? Here. So what if I said, I want you to find the equation of the line tangent to, let's make it not terrible to start off with, y equal to x cubed plus 3x at x equal to 1. So to find an equation of a tangent line, we need a couple pieces of information. We need, in fact, to find the equation of any line, you need two pieces of information. We need a point and a slope. We have half a point. We have the x part of the point, but we need the y part too. So our point is going to be, well, if x is 1, y is going to be 1 cubed plus 3 times 1, which is 4. So our point's 1, 4. To find the slope, well, that's where we use calculus, right? The slope of the tangent line is another way of interpreting the derivative. So we're going to take the derivative, and there's lots of ways to write it. You could write y prime. You could write dy dx, same thing. And that's going to be, let's see, it's going to be 3x squared plus 3. So that's the derivative everywhere, but I want the slope of the tangent line specifically at this one point. So then I'm going to take the value of x and plug it in. And you can either write that as y prime of 1, or some people write it as dy dx evaluated at x equal to 1, just to kind of show off some of the different notation you might see. And that's going to be 3 times 1 squared plus 3, which is 6. So now we have a slope, it's 6. We have a point, it's 1, 4, and we can use those two pieces of information to find the equation of the line. And you can, my preferred way is to use the the point slope form. You can use whatever form of a line equation you like, though. I like the one where you do y minus the y coordinate equals your slope times x minus the x coordinate you have. So in this case, it's going to be y minus 4 equal to 6 times x minus 1. And then I would probably go ahead and solve for y. So y minus 4 equals 6x minus 6, and then add 4 to both sides to get y equal to 6x minus 2. That would be the equation of the line tangent to this function at that point. And I could try to be slick, but I'm not. Yeah, I'm not that slick. I was going to try and show you on Desmos, but that would require hooking up some more chords and stuff. And I think you all just know, you can believe me. We could try to graph it a little bit, but no, it's going to look terrible. Let's not. Oh, I lied. Let's do it. Here's kind of what the graph would look like. And then here's my tangent line at the point 1, 4. The slope of 6. Seems believable. Yeah. All right. Let's up our game a little bit. Make it a little bit harder, but still kind of the same. So now what we're going to ask is to find the equation of the line tangent to the following. Let's say x cubed y plus x squared equal to 9x. Let me see here. 1, 2, 3. 9x minus. Trying to make sure the numbers are like not terrible here. Sure. 1, 2, 3. Sure. 3y. Hmm. 9x. Sure, fine. That's fine. So this looks kind of terrible, although not that terrible. If you really, really wanted to, you could totally solve for y here. That's not the point. And I could have made it so you couldn't. Oh, I need to give us a point though. So I'm gonna make that squared so we really can't solve for y. And then we're going to say at the point 1, 2. Let's make sure the numbers work. 2, 3, 9. Yeah, let me add on a 6 here. Sorry, you need to fix it. It's not really that important, but like, I don't want to write a wrong thing in front of you. So now it's right. Otherwise, that point isn't really on the graph. So this is a graph. You could totally graph this on Desmos, which is kind of cool. Like you can, this is a weird not function, right? If you graph this, you're going to fail the vertical line test for sure. But it still has tangent lines, right? Things that are not functions still have tangent lines. And so the way you would find the equation of the tangent line here is by using implicit differentiation, where we're going to assume that y is a function of x. So when I take the derivative here, I'm going to do all my usual kind of rules, but I'm really thinking that y is like f of x. Okay, so let's see. When I take the derivative of x cubed times y, I'm going to use the product rule. And I'm going to have the derivative of x cubed times y plus x cubed times the derivative of y. Derivative of x squared is going to be straightforward. It's going to be 2x. Derivative of 9x is not too terrible. It's going to be 9. The derivative of negative 3y squared, I'm going to say, I'm going to leave it for a second. I'm going to say it's just the derivative of negative 3y squared. And then the derivative of 6 is 0. All right, let's simplify this a little bit. This is where things are going to get interesting. Derivative of x cubed is 3x squared. That's why. Now, it's going to be, this is kind of a dumb question because the answer is the thing I'm about to say. What's the derivative of y? It's the derivative of y. So the derivative of y is the derivative of y. I'm using this process to solve for the derivative of y. So I want to have that show up. It's a little dicier over here. What's the derivative of 3 times y squared? Well, we need to think of this like a chain. Really, this 3y squared is 3 times some stuff squared. I might close that door. What's the derivative of some stuff squared? Well, chain rule, the derivative of this is going to be 3 times, let's see, the 2 comes down, you get 2 times your stuff to the first power. That's the first power, not a derivative, sorry. And then what do we multiply by when you're using the chain rule? The what of the stuff? The derivative of the stuff, always. So in this case, the derivative of 3y squared is going to be 3 times 2 times y to the first times the derivative of your stuff times y prime again. So that's going to end up being 6y times y prime. If we're making the implicit assumption that y is a function of x, then whenever you differentiate something with y in it, you're then having to multiply by y prime. Yeah.
For the very first part, where it says 3x squared y, why didn't you take the derivative of that y?
Well, because I was using the product rule there. So the product rule is telling me, right, if this is like my u and this is my v, then the product rule says I'm going to do u prime times v left alone plus u left alone times v prime. That's what's going on there. So now, yeah. So now there's kind of 2 ways you can go. I'm going to kind of go the long way just to show you how the short way also works. So I now want to solve for y prime. So let's see here. I've got this term and this term that have a y prime in them. So I'm going to collect them on one side and collect all the other terms on the other side. So I'm going to have x cubed y prime plus 6y times y prime equal to 9 minus 3x squared y minus 2x. All right, did you replace y1 with 4? No, I think, that was, sorry, that was back before. I apologize. Sorry, I don't always see the chat stuff right away. So I did replace y1 with 4. Yeah, that's what happened in that previous problem. Sorry, yes. Because I was using this point, and that's my x1 value, and that's my y1 value. Sorry, if you have a question that I don't see right away, you're really, really, really welcome to unmute yourself and say words. And I do think I have my volume on, so I should hear you. It just might terrify me, but it's okay. So if we're solving for y prime here, we're going to factor out the y prime, and we're left with x cubed plus 6y equal to all this stuff over here. And then finally, y prime is equal to all that stuff over there, 9 minus 3x squared y minus 2x divided by x cubed plus 6y. So there's your derivative in terms of x and y. I know it looks gross. And then, since we're trying to find the equation of a tangent line, we can use this derivative and this point to find the slope. And I didn't really leave myself enough room, so I have to use another page. It always feels kind of like a letdown. So our point was the point 1, 2, and our derivative is 9 minus 3x squared y minus 2x over x cubed plus 6y. So our derivative evaluated at that point is equal to 9 minus, let's see, I'm plugging in 1 for x and 2 for y. So 3 times 1 squared times 2 minus 2 times 1 all over 1 cubed plus 6 times 2. So I end up getting something not nice. It's going to be 9 minus 6 minus 2 over 1 plus 12. So let's see, that's going to be 3. It's going to be 1 over 13. Then we can use our point and our slope to find the equation. Y minus the y coordinate equals your slope times x minus the x coordinates. And then we can simplify. Y minus 2 equals 1/13 x minus 1/13. We can add 2, which is 26/13, and get 1/13x plus 25/13. It seems like a lot of work. There is one shortcut we could have taken. Is it a shortcut? Yeah, it's a shortcut. So if you go back to where we had just taken the derivative right here of both sides, right? We hadn't actually found y prime yet because we hadn't done all the algebra. But if you're doing this kind of implicit differentiation problem and you're just being asked to find the slope of a tangent line and not actually the derivative in terms of x and y like we did over here, right? We weren't actually ever asked to find this. No one said, hey, find the derivative. Someone said, find the slope of the tangent line and then use it to find the equation of the line. So what we could have done here is we could have plugged in 1 for x and 2 for y right there. Check this out. If I have that my equation after I differentiate both sides is this, 3x squared y plus x cubed y prime plus 2x equal to 9 minus 6y times y prime, and I'm looking at the point 1, 2, I'm going to plug in 1 for x and 2 for y. So I'm going to get 3 times 1 squared times 2 plus 1 cubed times y prime plus 2 times 1 equal to 9 minus 6 times 2 times y prime. And simplifying things, 3 times 1 times 2 is 6. 1 times y prime is y prime. 2 times 1 is 2. 9 and 6 times 2 is 12 y prime. So adding the y primes to the left, I get y prime plus 12 y prime, which is 13 y prime. 6 plus 2 is 8, and 9 minus 8 is 1. So y prime is 1/13, which is exactly what we got for the slope. I'm sorry, you can't see that. Let me know if you can't see the thing. So that's another way to do this sort of problem without doing all of the terrible algebra, is if you're just trying to find the slope of a tangent line and you don't care what the derivative actually is in terms of x and y, you can totally just plug in this as soon as you take the derivative. Which is kind of nice. Okay, all right. Yeah, we should go there. Question, yeah. Which this is what we did right here.
Yeah.
Let's do another example.
I feel like, why did you do that?
Well, so that's a good question. Why would I do it this way instead of the way I did it before? Well, I would say it's really kind of a matter of preference. If I only have to find the equation of the tangent line, I don't really need to know what y prime is. I certainly could find y prime, right? We did, and then we plugged in, then we plugged in the point 1, 2 and got the slope to be 1/13. But what I'm trying to say is that if you want to avoid doing all that algebra, right after you take the derivative, you can just plug in the point that we're trying to find the slope of the tangent line at. And then, in my opinion, it's less ugly to deal with. Maybe I'm mistaken, right? Maybe you think it's less terrible to do the other thing, but this is often a route people take, is to be like, oh, I'm differentiating, and then I'm just going to plug in 1, 2 right away to solve for y prime.
So when would you do it the longer?
That's a good question. So the reason you might do it the longer way is if someone just asked you to. I mean, there's not really like, so someone might say, for example, here, this is kind of a classic example, for x cubed plus y cubed minus, what is it, 327 minus 6xy, or equal to 6xy. Sure, people write it that way too, right? Find dy dx in terms of x and y, I should say. So this question, you can't just do the other thing because you're not being asked to do the other thing, right? We're being asked to literally find the derivative in terms of x and y and then write it down. So I kind of want to make you all do it. So here's what we've got. You've got x cubed plus y cubed. I'm going to think of 6xy as 6x as times y. So now I want you all to differentiate both sides of this. And remember, y is a function of x, or at least we're pretending like it is. So when you differentiate y cubed, you're not going to just get 3y squared. There's going to be something else there too. So let's take a look. If I differentiate x cubed, I definitely get 3x squared. And I really should use, I guess, more language here. I'm differentiating everything with respect to the variable x. So I'm asking, how is x cubed changing as x is changing? And the answer is, well, the derivative of x cubed is 3x squared. On the other hand, when we take the derivative of y cubed, we're going to get 3 times some stuff squared times the derivative of your stuff. I'm thinking of y as more complicated than just x. Y is a function of x. If it helps, you can totally do this. You can say what I really have is the following. I have x cubed plus a function of x cubed equal to 6x times a function of x. And so now when I differentiate it, it's a little more, I don't know if obvious is the right word, but it's a little easier to see that I need to use the chain rule. Right? If I'm going to differentiate both sides, the derivative of x cubed is 3x squared. The derivative of some stuff cubed is 3 times my stuff squared, but then I have to multiply by the derivative of the stuff. Same thing on the right hand side. Well, similar on the right hand side. The derivative of 6x is 6 times f of x, product rule, plus, do it the other way. 6x times the derivative of this is f prime of x. But instead of writing so many letters, we decided to use y instead of f of x. Yeah. That's a big question to answer. So the not satisfying answer is going to be whenever it applies. But really the answer is basically whenever you have a function of a function and the insides are more complicated than just x. So and I'll let's finish this and then I'll give you an example of that really quickly. But yeah, so the chain rule basically, if the argument of your function or the inside of your function or the thing you're taking the function of is more complicated than just a single x, you kind of have to use the chain rule every time. There's a couple exceptions to that, which we'll talk about, but most of the time, yeah, the chain rule is in play. So this is the same thing as that, except instead of writing y prime, I've written f prime. Instead of writing y prime, I've written f prime. But they're really the same, just another way of seeing it. So if we're now going to do the rest of this is so we've done all the calculus this problem requires. Yes, you totally could write dy dx as well. That is something people often do. I never feel like writing that because it's more writing, but yes, dy dx is also an option. So y prime, dy dx, f prime of x, they're all ways of writing the derivative. And people unfortunately kind of very easily flow back and forth between them. So you are probably going to have to be comfortable with seeing people write it in different ways often. The rest, so again, we've done all the calculus this problem requires. The rest is algebra. So I'm going to group the things that have the thing I'm trying to solve for together. So specifically this term and this term I want on the same side. It doesn't matter which side they go on. I'm going to bring them to the left. So I have 3y squared times y prime minus 6x times y prime. Well, I didn't actually finish this part. The derivative of 6x is just 6. So that's going to equal 6 times y minus this part here. Then we do more algebra. We factor out the thing we're trying to isolate, which is y prime. So we're left with a 3y squared minus a 6x, still equal to 6y minus 3x squared. And finally, we divide by whatever is multiplying y prime. So y prime is going to equal 6y minus 3x squared all over 3y squared minus 6x. And usually this is the end of the road. In this particular problem, you can do one more small simplification, which is factor out a 3 from the top and the bottom and cancel it. It's not a huge deal, but it is worth noting. You have 2y minus x squared over 3 times y squared minus 2x, and those cancel. So you really get y prime equal to 2y minus x squared over y squared minus 2x. It's kind of neat. So let's talk more about the chain rule. Because the chain rule is super duper important. And it definitely, so you're very, very soon going to learn about anti-differentiation, and integration. And one of the main methods of integration is what's called U substitution, which is really just like the reverse chain rule. You're kind of undoing what the chain rule does. Just like integration is integration is undoing what differentiation does. So let's look at some more examples. I've got so many examples over here. So let's start off with something that doesn't suck. My function is the square root of x, which is x to the 1/2. There's no need to use the chain rule, although technically you could. But not, well, in fact, yeah, we will. So I want to take the derivative, I'm going to use the power rule. My derivative is 1/2 times x to the 1/2 minus 1, which is negative 1/2. Now, if I really want to think about using the chain rule, listen to my words for a second. I have some stuff, I know it's just x, to the 1/2 power. And the derivative is 1/2 times my stuff to the negative 1/2. And then if I'm using the chain rule, what do I always have to multiply by at the end? Exactly. And what's the derivative of x? Right. So technically, you could always think that you're using the chain rule. It's just that a lot of the time you'd be multiplying by a 1, which isn't going to change anything. This would be 1/2 times x to the minus 1/2 times 1, which is just 1/2 x to the minus 1/2. Worth noting here, sometimes people write this like this. Sometimes people like to write this like this. They are the same, they just look different. Now, let's change it up a little bit. What if my function was the square root of x plus 3? Or preferably x plus 3 to the 1/2. Well, then I do need to think about the chain rule a little bit more. So I have some stuff to the 1/2, and my derivative still going to follow the same sort of rules. It's going to be 1/2 times my stuff to the negative 1/2, and then I have to multiply by the derivative of my stuff. What's the derivative of my stuff now? Still 1, right? The derivative of x is 1, the derivative of 3 is 0. So the derivative of x plus 3 is 1 plus 0. So this really actually, although technically we should be thinking about the chain rule here, you could kind of still ignore it. Now, let's make it even more fun. What if our function was something like the square root of x squared plus sine of x? Or preferably square root of, write the same thing again, James, or x squared plus sine of x to the 1/2 power. Now we really do have to use the chain rule. So when I take the derivative, I'm still doing the derivative of the outside function. I'm leaving the inside limit. So that's always kind of the gist. We're saying I have some stuff raised to the 1/2 power. The 1/2 power is my quote unquote outermost function, is the thing that's happening, for lack of a better word, last. But we have to kind of reverse order and deal with it first. So I've got something raised to the 1/2. The derivative of something raised to the 1/2 is 1/2 times that something to the negative 1/2. The inner stuff stays the same, but then when you multiply by a thing, you multiply by its derivative. So the derivative of x squared plus sine of x is 2x plus cosine of x. So back to what I was saying before, we need to use the chain rule when the inside stuff is more complicated than just x. Technically, you could extend that statement to the inside stuff is more complicated than just x plus a constant, because x plus a constant will still have a derivative that's 1. But you still think about the chain rule there. Time, okay. Time just flies by on this stuff. So let us do a few more examples. We should start talking about the other 2 derivative rules that you're going to learn very shortly. If you haven't, I mean, you might have seen them already in your last class, but they are the following. The derivative of e to the x. The best derivative ever. To e to the x. Kind of crazy. And the derivative of the natural log of x is 1 over x. And maybe next class we'll devote a little more time to talking about where these, like how these are actually derived, although we might not. We do want to know how to use them. So when I think about the derivative of e to the x, I'm really saying e to the stuff. In fact, whenever I'm thinking about a derivative rule, I'm usually thinking of it in the chain rule version. So some people like to write this and then the chain rule version of it, which is, your book probably uses a u. So they say the derivative of e to the u is e to the u times du dx, or they say it's e to the u times u prime. I really don't like writing it like that. Like, I just feel like it's not super helpful. I would prefer to say the derivative of e to the f of x is e to the f of x times f prime of x. Or really, honestly, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. Right? That's what we're actually doing. So every rule works like this. If you know what the derivative of a function of x is, the derivative of that same function of some stuff is just the same derivative, leaving the stuff alone, and then you multiply by the derivative of that stuff. So for example, the derivative of e to the 6x. Well, I know the derivative of e to the x is e to the x. The derivative of e to the 6x is e to the 6x. That's kind of the nice thing about any exponential derivative, like e to the something or 2 to the something, is the same function always shows back up untouched. But then, what do we need to multiply by? Right, what's the derivative of 6x? Right. And I would probably write this as 6e to the 6x. Right, we have to write the constant in front. Or the derivative of e to the, I don't know, x cubed minus cosine of x. Well, same idea. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. So here we're going to get e to the same exact stuff multiplied by the derivative of that stuff, which is 3x squared. The derivative of cosine is negative sign, so minus cosine will have a derivative that is minus sign, which is plus sine of x. Works that same way for the natural log, works the same way for all the functions, right? So just kind of, before I go this way, let me go quickly over here, right? Sorry, and I'm like, right, it works for anything else, right? So if I want to find like the derivative of cosine of x to the 5th plus tangent of x, I know the derivative of cosine of x is negative sine of x. So the derivative of cosine of some stuff is going to be negative sine of that same stuff. And of course, I've said the magic word stuff. So what do we have to multiply by? It's all right. It's always the same. It's always the derivative. It's always the thing. The derivative of stuff. Always. So it's going to be times 5x to the 4th plus the derivative of tangent is secant squared x. Sometimes they get a little more complicated. Sometimes you might have to use the chain rule more than once. For example, if I wanted to find the derivative of, I don't know, let's make it weird, tangent cubed of x to the 7th minus e to the x. Ooh, what's the outermost function here? Is it taking the tangent of something or is it cubing something? This is the cubing something. This is an abbreviated notation. When you have to take a derivative of a trig function to a power, I often recommend rewriting it in the long form, meaning you have tangent of x to the 7th minus e to the x, and it's all of that to the 3rd power. Now it's a little easier to see that being raised to the 3rd power is kind of the last thing that's happening. So that's my outermost function. That's what I'm differentiating. So I'm differentiating some stuff cubed. So the derivative of some stuff cubed is 3 times my stuff to the 2nd power times the derivative of that stuff. Which I haven't done yet. But now we have to take the derivative of tangent of x to the 7th minus e to the x. And that's going to require the chain rule again, because I have tangent of some new stuff. So the derivative of that's going to be, let's see, I've still got this part out here. That's not going anywhere. We still got 3 times tangent of x to the 7th minus e to the x quantity squared. And then the derivative tangent of x is secant squared of x. So the derivative tangent of some new stuff is going to be secant squared of that new stuff times the derivative of that new stuff, which is 7x to the 6th minus the derivative of e to the x is e to the x. Do make sure that when you're writing that down, you're actually thinking about the fact that it's becoming its derivative, right? It's not the same function. I mean, it is the same function, but it's the derivative of it, which is still the same function. It's kind of weird, right? That e to the x is its own derivative. Here's what that means graphically. It means on the function e to the x. Let's draw this up over here. On the function e to the x. Sure. However high the function is, that's the slope of the tangent line at that point. So like at this point right here, at 0, 1, the slope of the tangent line is 1. Over here, where the height's like 9, the slope of the tangent line is 9. Right? Whatever the height of the function is, that's also the slope of the tangent line. It's kind of neat. It's kind of weird. It's the only function that has that property. That's not entirely true. Okay. It's the only type of function that has that property, because technically any multiple of e to the x is also its own derivative. So like if you have 6 e to the x, the derivative of 6 e to the x is 6 e to the x. There is one other very lame function that is its own derivative. The function 0. Right? If your function is y equals 0, its derivative is y equals 0, which is technically a multiple of e to the x. It's 0 times e to the x. So still falls into the same category. All right, let's look at the other side of this page, the natural log side. So, whoops, might want to see the top part. Derivative natural log of x. Oh, question, yeah.
That's the end of the problem.
Yeah, for sure. So, derivative natural log of x is 1 over x. The derivative natural log of some stuff is 1 over the stuff. So for example, the derivative of the natural log of x to the 7th plus the square root of x is going to be 1 over that stuff times the derivative of that stuff. Now, usually people write that just on top. I'm kind of in the habit of not doing that, but you could totally be like, oh, I'm going to write that derivative on top and say it's going to be the derivative of x to the 7th is 7x to the 6th. The derivative of x to the 1/2 is 1/2 x to the negative 1/2, all divided by x to the 7th plus the square root of x. I know this looks gross, right? There's definitely some simplifying we could do if that was what we were interested in doing. It's not really the point though. Let's look at a couple more examples. Sure. Oh, okay. Maybe 1 or 2 more examples. There we go. I do kind of need to leave on time, I guess, because I'm supposed to go with office hours and it's a little bit of a walk. So let's look at the following. Oh, before I forget, I do also have some handouts. In case you want them, I'll put them over here. So you can on the way out. There's some handouts for practice problems and some derivative problems with the answers on the back. I don't think I have answers to this one, but I can write them up and post them on Canvas. So if you want to get extra practice with this derivative stuff, there's extra practice to be gotten. And yeah, I'll write solutions to this. Write myself a note so don't forget. Yeah, you'll work out. Let's see. I want to find the derivative of the natural log of x to the 4th plus e to the 7x. Okay, so derivative is going to be 1 over my stuff times the derivative of my stuff. So the derivative of my stuff, let's see, the derivative of x to the 4th is 4x cubed. And the derivative of e to the 7x, I'm going to have to use the chain rule. Right, the derivative of e to the stuff is e to the stuff times the derivative of that stuff. And then you could write it on top. I don't think we need to. Right, but if you prefer, people really do prefer 4x cubed plus 7e to the 7x over x to the 4th plus e to the 7x. Ooh, yeah, let's do one more. Yeah, one more good one here. Let's say I want to take the derivative of the natural log of what's the base for natural log? Yeah. Well, just e. Yeah, just e. So really, when I write natural log of x, it is really log base e of x. It just comes up so much that we don't write the log base e. Let's say I had x cubed times the square root of x squared plus 9. Yeah. I could do it that way, right? I could be like, okay, it's gonna be 1 over the stuff times the derivative of the stuff. But then the derivative of the stuff, I have to use the product rule because it's x cubed times the square root of x squared plus 9. And I also have to use the chain rule. Seems like a lot of rules. Here's what I would encourage you to do if you ever see natural log or any log of a complicated thing that's multiplied or divided together. We can use the rules of logarithms, right? There are some rules of logarithms, like the fact that the natural log of a product is equal to the natural log of the first thing plus the natural log of the second thing. So I can break this up and write it as, I'm not taking the derivative yet, I'm just rewriting the function, the natural log of x cubed plus the natural log of the square root of x squared plus 9. And then I can use another logarithm rule, which says if you have the natural log of something raised to a power, you can bring that power down in front. The natural log of m to the p is p times the natural log of m. And so I can bring that 3 down in front and say my function is 3 times the natural log of x. And this is a power as well, right? This is x squared plus 9 all raised to the 1/2 power. So I can bring that 1/2 power down in front. So I have 1/2 times the natural log of x squared plus 9. And I can't simplify anymore. I can't bring this power of 2 down because it's not a power of 2 on the entire argument of the logarithm. So you can only bring the powers down if everything in the logarithm is raised to that power kind of at the end. So I'm stuck with that. So now I do just need to take the derivative. So my derivative is going to be 3 times the derivative of the natural log of x is 1 over x. And if I haven't said this before, I'm going to say it right now. When I'm thinking about taking the derivative of a constant times a function, the constant just hangs out. Right? Constant multiples just hang out, and we take the derivative of whatever they're multiplying by. Same deal here. This 1/2 hangs out, and the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff, which is 2x. And I suppose if I was in a simplifying kind of mood, I would cancel a 2 here and a 2 here and write this as 3 over x plus x over x squared plus 9. Kind of tiny. And just to fill in the last logarithm rule that you should be aware of, maybe not the last one you should be aware of, but the one that kind of fits in with these other two is the natural log of a quotient is equal to the natural log of the top thing minus the natural log of the bottom thing. All right. It's 3 o'clock. We should call it a day. I should head over to the south silo for the first time in my life. Not my life.